In the last video, we discussed the idea of numbers that could have multiple representations in floating point forms. So for example, we had the number 25, which we were representing with the following. We had a signed bit of 0, we had an exponent of, say, 20, and then we had the value of 25, right? Basically, the idea was that when we have the decimal here, we can move it over 5 places and we end up with 25. However, we could also shift this number over, so we could end up with something like 0, 1, 1, 0, 1, 0, 0. And in this case, we just have to shift the decimal over 6 places rather than 5. We would end up with the exact same value. This is not ideal. Most numbering systems, we want one representation for each quantity. So we want to try to fix this problem. To fix this problem is actually fairly straightforward. It's a process known as normalization. And the idea with normalization is that we set up the significand in a very specific format. Basically, we always have a leading one followed by a decimal. Then we have the rest of the value. This ensures that the decimal is always in a consistent space. That's because with this problem here, basically the reason why this problem exists is because we can get leading zeros in front of the number. If we can't get leading zeros because there's always a leading one, then we can only have one representation of the number itself. So that allows us to solve this problem. So that's generally the idea of normalization. Now, with normalization, there's another interesting benefit that we get out of this. And that's that if the value that leads is always a 1, we actually don't need to store it anywhere. We could simply just place it whenever we need to do any sort of conversions, and we'll be able to do that because we know that there's always a leading 1. So actually what ends up happening is we get an extra bit as well on this left-hand side. So that's another little benefit. So rather than having 8 bits in this example, we would actually have 9 bits available to us. So let me show you how that representation generally is going to look. Basically, this number here, the 11001,000, what it turns into with normalization is it turns into 1001,0000. And there's this 1 on the left-hand side that's assumed to be there. So do you see that we don't actually store this 1? I'm putting it in brackets to say it's not actually stored, but it is there. It's like an imaginary value, right? So because this value is always there, we don't actually store it. We just assume it to be there. From here, we simply take this decimal, we move it over 4 spaces, and we get 25, and this is the only representation of 25 that we have available. So that's all great. So this is the idea of normalization. Now, one question that sometimes comes up with this is, what about representing 0? There's always a leading 1, so how do we actually represent 0? And the answer is that we just define it to be a specific value. So we say it's going to be 0 with the sign bit, 0 with the exponent. Then we have our leading 1, but then the rest of everything else is all zeros, right? That's how we define 0 for this particular instance, is we just say the exponent is 0, the sign bit is 0, everything else is 0. The assumed 1 is still there, but because we're saying that this is 0, well, we can just ignore that and define everything as 0, right? Basically, the idea here really mimics that idea of, something raised to the exponent 0 is equal to 0. But in this case, because we're this leading 1, it's technically not, but we just define this as 0 and use that representation. So that's just something to look out for when we're working with this kind of floating bit format. So from here, let's move over to IEEE floating point and discuss how that actually is done. IEEE floating point, very similar to the floating point notation that we talked about earlier. Basically, the main thing that changes is the size of everything. So the sign bit is still going to be 1 single bit. What changes is that the exponent is now going to be 8 bits in size. And the significand is going to be 23 bits. This gives us a total of 23 plus 1 is 24, plus 8 is 32 bits. This is a floating point number. Now, you probably know that there's also the idea of a double in most languages, and this would be a 64-bit floating point number. Same sort of idea, just these two things get bigger. Right? So same process, same sort of setup, just those values are going to get generally bigger. That's how you usually get from floating point to double. So from here, let's discuss the idea of how we can represent some numbers. I want to give you a really simple example. So let's say 0.5 we want to represent as a floating point number. First things first, sign bit, nice and easy, that's going to be 0 because this is a positive number. It's going to be equal to 0. If it were negative, it would be 1, right? The next question that we have here is, what about the exponent? What about the significand, right? What do we do with these two values? First thing I recommend doing is taking a look at the significand. We want to understand, how do we represent 0.5? Well, 0.5 is just 2 to the power of negative 1, right? So what I want to do is I want to get a decimal 1, right? So 0.1000 is going to be basically my representation of 2 to the negative 1, or 0.5. So to do that with our significand, all we really do is we say there's this invisible leading 1 here, decimal comes after it, and we have a bunch of zeros right after that, right? So that's all great. From there, we just need to get a negative exponent. So an exponent of negative 1 to move the decimal over to the left 1 space, right? With the exponent, things change a little bit. So in the previous example, you saw that we were able to do it based on, that 5-bit bias, right? Where we have, half of it being positive, half of it being negative. Because we have 8 bits now, we're actually working based off of what we would call a 127 bias. So basically the first values from 0 to 127 are going to be our negatives up to 0, and the 127 onward up to 256 is going to be our positive exponents. So to get to negative 1, we need to be able to store 126 of this, since 126 minus 127 would give us negative 1. So that gives us 0, 1, 1, 1, 1, 1, 1, 0. And that's all we need to do. From there, this becomes a negative 1, so the decimal moves over 1, that gives us 0.1, which is going to be our 0.5 in binary. That's all there really is to it, right? So you can see that understanding the basic floating point number, this becomes quite easy. The main thing to really watch out for is just this significand having this 1 in front of it, right? And what I'm going to show you in the next video is that when we take a look at this in C code, we actually decompile to GDB, we'll actually see that this value isn't stored. It will just be all zeros here. This will be the exponent, this will be the sign. This is something that catches people off guard sometimes because they don't know about this, mysterious 1 that's sitting in front. So just that's the main thing to be careful of. I'll show you that in the code in the next video when we go over that sort of process. So this gives you the base fundamental ideas of how IEEE floating point is generally working. So it's a nice simple representation, right? Just the exponent and significand are a little bit bigger. The significand is normalized, meaning that it has a leading 1. That's all we really need to keep in mind for that. For 32 bits, these are the values. For double, these values are just going to increase to match up to 64 bits. And that's really all there is to it. So with that, you can understand the basics of IEEE floating point numbers. In the next video, I'll show you this in the actual code itself. Then we'll be able to discuss some differing ideas around, representations of data. We'll talk about characters and strings. Then we can move into some more things that apply binary numbers, things such as like logical gates, that type of idea. So thanks so much for watching this video, and I'll see you in the next one.